Mr. Frank Götz. Yeah, floor is yours.
As soon as the presentation starts, I'm feeling a little bit challenged because usually I try to connect my presentation to the presentation from the presentation from before, and in this time it's a real challenge because it's a very trendy topic, AI in the construction industry, and now it's up to me to connect it with a very traditional topic in steel construction. It's about bolted connections, and I'm not sure if I will handle it, but anyway. I'm really pleased to be here in Istanbul. It's my second time in Istanbul. The first time was 6 weeks ago. So you can imagine that it's a very nice city and I like it to be here. So 6 weeks, tried 2 times. And today I will present you something about bolted connections, especially in a European context. There are a lot of changes right now in European regulations. A lot of the standards have been revised in this year. And there's a lot of ongoing about bolted connections, to be honest. And the interesting thing is, if you compare it with American standards, with European standards, and even in Japan, the basics is always the same. It's a bolt, it's a nut, the technical, the mechanics is equal. But due to the regulations in the respective country, we have sometimes bigger differences than we expect. And therefore, I want to give you a short overview about what's all going on in Europe. Yes, my name is Frank Götz. I work in several technical committees on a European level, on a national level. I'm involved in technical guidelines, everything around bolted connections. And my employer is the Nordler Group, which is a company out of the field of bolts, fasteners, and securing elements. So, the first thing we need to consider if we talk about bolted connections is always what kind of loads those bolted connections are subjected to. And if we consider, for example, here, if the pointer works, doesn't matter, the left picture, if we consider a very simple industry building in the middle of nowhere, it's also our production plant in the middle of Sweden. There's no sophisticated approaches to design it. It's a standard building. So we can follow our guidelines, we can follow the Eurocode 318. We have everything we need. So we have purely static loads on such a construction, on such a structure. If we move one picture forward to a railway with a noise barrier, then it's getting already a little bit more challenging, because now we have wind pressure, we have wind suction, we are talking about so-called quasi-static loads. So for our design rules are still static, but we know that those loads are more or less dynamic, which can complicate some things and especially the design. In the third picture, it's a crane substructure, a crane structure. Here we are talking about dynamic loads. We have vibrations, we have shock loads, and here we need to consider different design approaches than we have considered them on the first and the second picture. And I would say the biggest challenge, if it comes to bolted connections, bolted joints, bolts, nuts, whatever, is I think at the moment in the wind industry, and now I tried, there even AI is playing a big role right now, because the wind OEMs are evaluating the flanged connections also with AI to build a forecast for the upcoming maintenance intervals, for example. And here we have everything which we as civil engineers, structural engineers do not like. We have very high dynamic loads, we have very high wind loads, we have a structure which is moving sidewards. That's really challenging. And therefore our structural design codes often are not sufficient. And there we take part of the mechanical engineering field. So the most common guideline there is, for example, the VDI 2230, which is about the design principles of high-stressed bolted connections. And then, getting back to the European standards, maybe my question to you, gentlemen and ladies, who is familiar to these European standards? 1, 2, 3, 4, 5, okay? So, in the design phase, or as a design engineer, the most relevant standard in Europe is the Eurocode 318 on the top. it's everything about the design and the verification process of bolted connections. So we can verify the bolt with the shear resistance, bearing capacity, but also we can pre-stress the bolted connections to create a slip-resistant joint. That's from this design perspective, but that's not helpful if we look to our bolted connections in a general approach. Then we also need to consider the EN 1090 Part 2, the execution of steel structures. And here we find different tightening methods, and depending on the country, some countries love to tighten the bolts with the torque method, sometimes it's more the combined method where we have a rotation angle, some countries are in favor of DTI washers. It really depends on the country where the structure is. Which could be interesting, especially for companies or engineers who are working globally, is the third standard, the ISO 17607. That's a very new standard, which is published also this year, and that's the first global standard, as an ISO standard, for the erection of steel structures. And Part 6 is exclusively for bolting. And that's interesting, especially if we compare the civil engineering, the field of civil engineering to the field of mechanical engineering. So for many mechanical engineers, it doesn't matter who is the supplier of the bolt and who is the supplier of the nut. In the field of civil engineering, we often talk about bolting assemblies. That means that the supplier of the bolt and the nut should be the same. We have an assembly. And the reason for this is that we want, or the supplier should take care about the maximum proof load the bolt assembly can withstand. And that's a big difference to the mechanical engineering, and that's why we have these two standards in orange and green, the EN 15048, which is for non-preloaded bolting assemblies, and we have the 14399 for high-strength structural bolting assemblies, namely HV, HR. And if you need to consider even larger bolts, then we have M39 to M72. They're a German guideline and a French standard, which also cover the bigger bolts in the construction industry. Getting back to the Eurocode 318, we find also five bolting categories. And on the left side, again orange, we call it non-preloaded connection. So for the top left example, we have a shear connection. We are verifying the bolt on its shear capacity and the structural parts on bearing, for example. A pre-tension of the bolt is, for the verification, not needed. So it's a non-preloaded connection. But in those cases, we often improve the level of serviceability of the bolted connections by applying a specific torque, maybe just snug tightening, maybe just anything, for reasons that we create a higher joint stiffness to reduce the slip in the connection, but also to close gaps that may cause any corrosion issue. So the design is made without a pre-tension, but we use the biggest advantage of a bolt, namely being pre-stressed. If we wouldn't use the pre-tension in a bolted connection or in a bolt, we could still use rivets, like in the past, because the bolt is made to be pre-stressed. And on the right side, the green one, it's the preloaded connection, and here we take advantage also in the design phase from the pre-tension of a bolting assembly. And if we look to the top right picture, we are tensioning the bolt, we are introducing a preload, a pre-tension in the bolt, and as reactio we have the clamp load. And the big advantage here is if we now have a shear load on the connection, it is not applied on the bolt. So the bolt does not see or feel or whatever any shear load which is external. It's completely independent. So the shear load will be transferred through the friction between the clamped parts. And if we have fatigue loads, that's the basic design principle which we should follow, always using preloaded connections. And therefore we need to guarantee that the preload which we use in the design phase is applied properly, EN 1090 Part 2 for example, and is also inspected, controlled, and maintained in the proper way over the lifetime of the structure. And if we can't guarantee this, we have one big problem with bolts: they may become loose. And just to give you an overview about the nomenclature, there's one topic: bolt becomes loose, and then we can defer it into a so-called slackening, which you can see on the left side, and a so-called self-loosening if we have vibrations on the structure as well on the right side. Slackening is also further divided into an embedding and a creep. Embedding means that during the tightening process, or even during the operation of the structure or the lifetime of the structure, the surfaces of the metal gets flattened. And due to this, we lose microns of clamp length. And microns of clamp length reduction means that we lose preload. And in the end, we have a loosened bolt. Much more critical for ourselves in the steel construction industry is creep and relaxation, mainly because of the corrosion protection of our structural parts. We have coatings on it, 200 microns, 300 microns, and when we tighten the bolt, this, you can see it on the picture before, the painting is just squeezed out, and therefore we lose clamp length, reduction of preload, and in the worst case, the bolt becomes loose again. And here, for example, that's how it should be done if you have a preloaded slip-resistant connection. The EN1090, for example, tells you that you need, or it's mandatory to reduce the coating thickness on every parting line. And many companies, and that's a very common mistake in the practice, many companies are reducing the painting on the connected parts. As you can see here, the gray area, that's just a very, it's 80 microns of small corrosion protection. And what many companies forget is also that you need to reduce the coating thickness underneath the washer. And the EN1090 is mentioning it. But anyway, in many cases, it's forgotten or not considered. The other phenomena is the so-called self-loosening. And self-loosening happen if you have a movement in the connection. That can be a high vibration like shown in the animation, but it's also possible if you have, for example, a thermal movement caused by the day-night shift. So the components are getting warm, we have some movement. It's just one load cycle or two load cycles each day, which may lead to a self-loosening of the bolt itself. And if you imagine the thread of the bolt unrolled, you will receive a ramp. During the tightening process, you just push the bolt up the ramp and you're tightening it. If now a movement happens, or if we overcome the friction, it's exactly happened what you see in the animation. The bolt becomes loose and it just went down the ramp. And on the one hand, the bolt rotates out of the blind hole, the bolt rotates out of the nut, or the nut rotates from the bolt, leading to problems. And that these problems are existing mention also the standards which we use in Europe. So we have the EN1090, which mentioned that especially a small ratio of clamp lengths relative to the bolt diameter is, shall use a locking method. We have the design Eurocode 318, where bolted connections which are subjected to shock loads or considerable loads of vibrations. We have a German standard for earthquake areas. Bolted connections in earthquake areas should use a securing method as well, and so on and so on. And the big challenge, especially for design engineers, is to decide when the load is considerable, because that's something the standard does not mention. And that's a little bit unsatisfying, but it is what it is. In the end, the design engineer is responsible to give a recommendation if a bolted connection should be secured or not, or if he has any design principles followed to make the bolted connection more durable and resilient. If not, these are very common examples of self-loosening, slackening. On the left side, we have the typical fatigue failure of a bolt because the pretension gets lost. And on the right side, we see the upper bolt completely missing, so the nut completely went down the thread of the bolt. And here on the lower picture, you see a partial loosening as well. The bolt is still in the hole, but you can imagine that in the next couple of load cycles, it won't transfer any loads anymore. So, how can we counteract this? By following some simple design rules. And the first is increase the pretension, increase the preload. How? For example, by using high-strength bolts, 10.9 instead of 8.8, or by choosing the right tightening method. Instead of DTI washer, instead of a torque method, maybe the torque angle method, or turn the nut method, or combined method. Doesn't matter how you call it, it's always the same. Applying in the first tightening step a torque, and in the second tightening step an angle. You can also increase the resilience by choosing larger bolts, larger clamp length, for example. You can reduce the slip, that's also a good recommendation. If you reduce the movement between the parts, you increase the level of durability. And of course, settlements. If you reduce the painting thickness, if you reduce the loss of preload in a connection, that makes your bolted connections more durable. And then if these design principles are not enough for your structure or construction or for your self-confidence, I don't know, then there exists a lot of securing elements on the market. And the problem with them is some work, some not. And looking to the very restricted environment of the construction industry, we are following standards, we have confirmed products. Here is an overview of items or articles which you should not use in the daily business. Because those securing elements like the spring washer, castle nut, pal nut, or methods like double nutting and thread deformation, the standards are withdrawn 20 years ago because they are not state of the art. In the meantime, even the standardization bodies know that those elements are not effective, they're ineffective, they don't keep the bolt tight, and therefore, please avoid them. A possibility of a securing washer is, in this case, surprise, one slide about a Nordlock, is a Nordlock washer, and the Nordlock washer is at the moment the only CE-marked securing element on the market. And the principle is as simple as genius. And if we talk about a washer, we have always on the outer surface so-called serrations, which create a form fit to the mating material, to the nut, to the bolt, and to the structural parts. And if we have this form fit, then the cams get active. And the principle, as mentioned, is very simple. The angle of the cams, alpha, is a little bit higher than the angle of the thread beta. Which means if the bolt wants to become loose again and you want to move down the thread, the ramp, first it needs to be stressed to come over the difference between alpha and beta. And stretching the bolt means increase of the pretension. Increase of the pretension means that the bolt do not want to become loose. It secures itself by the geometry. Very simple and effective. And there is a very common standard on the market. It's called the Chunker test. It's also regulated in an ISO standard, an DIN standard, EN standard, whatever. And this standard is putting a movement on the connection, a vibration, and if you want, on the way home back again or the next days, you can watch the YouTube video. It's just to compare different securing methods on their effectiveness. And finally, to give some examples where you should put some further thoughts into securing methods about your bolted connections. A very common example is noise barriers, as already mentioned. You have wind sanction, you have wind pressure, And there are a lot of damage cases, especially for these anchor bolts along the railroads. We have seen bolt failure, we have seen nuts coming loose, and that's along kilometers of tracks. So that's a very common problem. The next one is storage tracks. Storage tracks, as mentioned in the standard, we have very short clamp lengths. And usually a storage rack is not highly dynamically loaded, but if you have some robots moving in there, for example, or if you have some machines moving, then you have dynamic loads on the storage rack as well. Bridges as well, very common, but it's often not about the primary structure, it's often about the secondary structure, like pipes which are connected to the bridge, again barriers, lights for example, there we often find loosened bolts as well. Crane runways, crane substructures, very common. In my country, in Germany, it's in the meantime really state of the art. It's getting a standard to secure all the bolted joints, bolted connections at a crane substructure with the Nordlock washer. It's not a high quantity of washers, but the problem is obvious for those structures because we as structural engineers, especially those engineers who are designing those structures, are not very familiar to dynamic loads. And also coming more and more popular are facades, especially if we talk about filigree structures. It's getting more filigree, we have more wind loads, it's getting more complicated. In the meantime, we have more and more applications for facades and roofs as well. Hopefully I was in the time, and thank you for the attention.
Okay, thank you very much.